by the way, for anyone who just came back, I totally, in that last example, had a silly mistake, which was I totally forgotten which equation went which was the curve. So I thought, oh, this equation is at the bottom, so what's the curve on the bottom? No, this equation is the circle, so it's the curve up here. This equation is the parabola, so it's the curve down here, which means that these two formulas should have been switched in the final answer for that last example. One more minute and then I'll actually get started again. Okay, it is now 12:48, so I'm going to get started again. Again, unless I get through section 6.5 incredibly fast compared to what I'm expecting, I'm going to cut out section 6.2.4 as well. Because I don't, again, I'd rather spend more time to do with the stuff we're covering next week, which is more sort of real-world applications of these sorts of things. The next section, section 6.5, is the shortest section in chapter 6. It's called average value of a function. So the idea is the types of questions you're going to be dealing with in this section are things like, what is the average value of f of x equals x squared between x equals 0 and x equals 1? Does anyone here know how to do this already? One hand. How many people here have done this before and forgotten? Okay, a couple. People who've never seen this sort of thing before. It turns out that once you learn all the formulas, is really straightforward, and the key thing is just sort of understanding how do you calculate averages using integrals. So the thing I want to mention is you already should know from high school, at least, or elementary school even, one way of calculating averages, right? If you want to calculate the average of a bunch of numbers, you add them all up, you divide by the number of numbers you have, right? So if you have 10 different numbers, you add them all up, you divide it by 10, right? That's sort of the easy way of calculating the averages. The problem is this doesn't always work. It doesn't work when you're faced with a function which varies continuously with time. So for example, if you want to talk about the temperature over a day, the temperature is not exactly the same at any two times, right? If you take the temperature 1 minute and take the temperature a minute later, it's going to change slightly. It might not have changed enough for your thermometer to have noticed the difference, but it will have changed. If you want to calculate the average temperature in that day, you can't necessarily do it by just taking, 20 different temperatures, add them up and divide by the number 20. And the reason is because there are more than 20 different temperatures that happen throughout that day, right? Every minute has a slightly different temperature. So the reason that it's hard to compute the average temperature in this sort of situation is because temperature is something which is called continuous. It keeps on changing, it doesn't so in mathematics you have two different notions, the idea of something which is discrete or something which is continuous. Something which is discrete is something which is one number at one time, one number at the next time, one number at the next time after that, where there's no in-between times. Something which is continuous is something which changes from one time continuously through to the other time, where every time interval can be divided up into smaller and smaller pieces. And so in continuous situations, the way we're going to need to take the average temperature is with an integral. Yes?
Is there a handout for this one?
Oh, thank you so much. Yes, there is, and I totally just forgot to hand it out. Because I am scatterbrained. You're welcome. Thank you for asking. Okay. So, the idea is, well, we can't sort of calculate an average temperature by picking a bunch of things and adding them up. We can approximate the average temperature. Now, how are we going to approximate the average temperature? We're going to take the day over which we want to calculate the temperature, and we're going to divide it up into a bunch of different time intervals, say every minute. So we divide this day up into a bunch of minutes. Then in each minute, we pick a time at which to measure the temperature. that time at which we're measuring the temperature is going to be called the sample time. We measure the temperature at that sample time. That's going to be whatever the temperature function is. We're going to evaluate the temperature function at that time, measure the temperature at that time. And then you're going to add up all the temperature measurements and divide by the number of measurements. So what we're going to do is we're going to take each temperature measurement, we're going to add them all up, that's what the sum symbol means, and we're going to multiply by 1 over n, by 1 over the number of measurements. Now this turns out to be an example of a Riemann sum. And the reason is because delta x is the same thing as b minus a over n. Right? So I don't know if you remember this from section 5.2, but the length of those time intervals is the same as the length of the entire day divided by the number of time intervals. So delta x is b minus a over n. So if we have 1 over n, we can think about that as b minus a over n times 1 over b minus a. Or delta x times 1 over b minus a. So that means if we have this sum, this 1 over n can become a delta x times 1 over b minus a. So it's 1 over b minus a times this thing, and that thing is a Riemann sum. It's a sum of a value of a function a bunch of different times times the length of the time interval. So this sum can be replaced with an integral. So the idea is if we don't have to measure the temperature every minute, but we have a formula that predicts the temperature, right? So if we want to calculate the average temperature, what we can do is we can just integrate that formula and multiply by 1 over b minus a. So this formula here comes from the idea of what would happen if we measured the temperature every minute. We added those up, we divided by the number of temperature measurements, but that can give you a Riemann sum, which can be evaluated with an integral. So any questions about where this formula comes from before I go on to some examples of using it? Just want to mention that for the purpose of this course, memorizing that formula is fine. I'm not going to, for the purpose, yes, I'm not going to expect you to be able to derive it. That's what I was trying to say. I'm not going to give that one to you on the formula sheet, yeah. So you should know it, or else understand how to derive it from here. But most people just choose to memorize the formula. It's fairly straightforward. So if we want to calculate the average value of a function, we call this f_av for the average value of f. Again, if you're trying to calculate the average value of a function, we've always got to calculate its average value over some interval. For example, we could talk about the average temperature today, right, which means from midnight to midnight. Or we could talk about the average temperature during the daylight hours today, which would be from sunrise to sunset, right? Those would give you different averages. So you always got to specify what interval are we measuring the average on, right? And those are going to be your limits of integration. They're also the numbers that go into that 1 over b minus a in front. So let's suppose you want to find the average value of the function f of x equals sine of 4x on the interval from negative pi to pi. So the idea here, if f of x is sine of 4x, then f_av, the average value of f, is going to be the integral. Oh, sorry, it's going to be 1 over b minus a is pi minus negative pi, right? Integral from negative pi to pi, sine 4x dx. So the first thing to mention, in order to integrate this, not just sine x, we've got sine 4x, so we're going to need substitution to do it. We're going to pick u equals 4x, so du is 4 dx, so du over 4 is dx. Oh boy. When x is negative pi, u is negative 4 pi. When x is pi, u is positive 4 pi. Here, let me write that a little bit clearer. Negative 4 pi, positive 4 pi. So this thing in front will become 1 over 2 pi. Pi minus negative pi is 2 pi. Here we're going to have the integral from negative 4 pi to positive 4 pi. Sine 4x will become sine u. Dx will become du over 4. We can move the 1 over 4 out front. This constant in front will become a 1 over 8 pi. Here we're going from negative 4 pi to 4 pi. Sorry, I'm doing this thing where I'm blocking that side again. Sine u du. And then we just need to find the antiderivative of sine. The antiderivative of sine is negative cosine. So we're going to have negative cosine u from negative 4 pi to positive 4 pi. Why am my writing's getting worse? Negative cosine u from positive 4 pi to negative 4 pi to positive 4 pi. We're going to plug in those numbers and subtract. So we're going to have negative cosine 4 pi minus negative cosine negative 4 pi. Turns out that cosine of 4 pi is 1. Cosine of negative 4 pi is also 1. The reason is because 4 pi is just 2 complete revolutions. So both those situations give you back to the original spot in the unit circle. This is negative 1 plus 1, which gives you 0. Sorry, this constant in front I haven't been writing down. So here there should be a 1 over 8 pi. In front, here there should be a 1 over 8 pi. In front, here there should be a 1 over 8 pi. In front, it'll still give you 0, because 1 over 8 pi times 0 is 0. But this means that the average value of sine of 4x is 0. Now this completely makes sense, because if you draw the graph of sine of 4x, the graph of sine of 4x looks like this. The average value of this thing should be in the middle of the graph. Where's the middle of the graph? The middle of the graph is at 0. That's why the average value is 0. Half the time it's positive, half the time it's negative, which should make the average be 0. Any questions about this example? Okay. Example 2. Okay. Here we have the function g of t equals t over square root 3 plus t squared. And we're trying to find its average value on the interval from 1 to 3. So if we're going to do that, we're going to take 1 over 3 minus 1 times the integral from 1 to 3 of this guy dt. One over 3 minus 1 becomes 1/2. So this is the 1 here. Sorry, before I can complete the integral, I'm going to need to use substitution to do this. And again, it's because there's something inside a square root there. So I'm going to pick u to be 3 plus t squared. So du is 2t dt. Now we don't have a 2t dt here, we just have a t dt. So du over 2 is t dt. Also, when t is 1, u is 3 plus 1 squared is 4. And when t is 3, u is 3 squared is 9. 9 plus 3 is 12. So it'll become the integral from 4 to 12 of 1 over square root of u, and the t dt will become du over 2. The extra 1/2 can come out front. And if we want to integrate 1 over square root of u, that's u to the negative 1/2, The antiderivative of u to the negative 1/2 is u to the 1/2 over 1/2. And that goes from 4 to 12. Divided by 1/2, same thing as multiplying by 2. So this 1/4 will become a 1/2 once we divide by 1/2. We're going to plug in 12. We get 12 to the 1/2. Plug in 4. We get 4 to the 1/2. 12 to the 1/2 is just square root of 12. 4 to the 1/2 is square root of 2, which is just 2. And you can leave it like this if you want. Square root of 4, which is 2, sorry. This is the average value of that function on that interval. Any questions about example 2 here? So this is how you compute average values. You got a function, you got an interval, you do 1 over b minus a, then you integrate the function. And that'll always give you the average value of that function. Now the second half of section 6, I've got example 3 to go through first. Sorry, I forgot which slide I was on. Before I get to the second half, I just want to talk a little bit about what happens when we talk about applications of average value. One of the things they can do with average value is ask you to calculate the average value of something which has a real-world application. So here is an example. It talks about the velocity of blood that flows in a blood vessel. It changes between the outside of the blood vessel and the inside of the blood vessel. It varies with the radius and the length of the blood vessel at a distance r from the central axis. So the central axis of the blood vessel is in the middle of it. So how far out it is, it changes the velocity. And that's the formula for the velocity. So now they want you to find the average value of the velocity. What's the average velocity between 0 and capital R? And here saying lowercase is between 0 and capital R. Lowercase r is between 0 and capital R. That means lowercase r is your x in this problem. Lowercase r is going to be the thing you're going to be integrating with respect to. So here's example 3. Okay, so here the function is, v of r is p over 4 eta L capital R squared minus lowercase r squared. And we're going over the interval from 0 to capital R. So if we want to calculate what this is going to be, what we're going to do is we're going to take 1 over capital R minus 0, that's your 1 over b minus a here, the integral from 0 to capital R of this thing, p over 4 eta L capital R squared minus lowercase r squared d lowercase r. Again, because it's a function of lowercase r, we're integrating with respect to lowercase r. So I can take this p over 4 eta L, it's just a constant, it has no lowercase r's in it, so I can pull it out front. So here we'll have p over 4 r eta L. All right, just taking the 1 over r that I'm going to get and multiplying by that constant I can pull out front. Here we're going to have the integral from 0 to r squared minus lowercase r squared dr. Next thing we've got to do is integrate these two guys. Integrate this guy, find their antiderivatives. Now, here we're integrating with respect to lowercase r, which means that capital R is a constant. It has no lowercase r's in it. So the antiderivative of capital R squared is just going to be capital R squared times lowercase r. Right? If we took the antiderivative of 4, it would be 4 lowercase r. If we took the antiderivative of 12, it would be 12 lowercase r. If we took the antiderivative of capital R squared, it's going to be capital R times lowercase r. Sorry, I'm switching colors just because the black is getting a little bit low. 4 capital R eta L. So here, when we integrate that, it's going to be capital R squared times lowercase r. Here, if we integrate lowercase r squared, it'll be this, lowercase r cubed over 3, all from 0 to r. So then we've just got to plug in and subtract. So we've got p over 4r eta L We plug in capital R, we're going to get capital R cubed minus capital R cubed over 3. We plug in 0, we get 0 and 0. Both those two things. Plug in lowercase r equals 0. So this thing minus this thing over 3 is 2/3 of this thing. So it's P over 4R eta L 2/3 R cubed. One of those r's is going to cancel, and so we'll get 2p r squared over, oh, sorry, the 2 is going to cancel with part of the 4. So we get pr squared over 2 eta L. No, 6 eta L. I don't know how to. 2/3, like the 4 on the bottom will make this 2/12. 2/12 cancel the 1/6. On the top we have a p and the r squared from here. The bottom is the 4 and eta and, or sorry, 4 times 3 is 12, cancel with the 2 to give you 6, and eta and an L. I'm going to write that a little bit better. P r squared 6 eta. Eta is that weird Greek letter that looks sort of like an N. And you don't have to know the names of these guys, as long as you can sort of write it. It's fine. Sorry, to compare the average velocity with the maximum velocity, I'm not going to bother with that. I wouldn't ask for that on a test. I just ask you to find the average velocity. Yeah. Any other questions about this before we move to the next section? Okay. So the last thing we're covering this week, which is also going to be the last thing that's on the quiz on Tuesday, is 6.5.2, which is called the mean value theorem for integrals. So, I mean, this is the sort of question it answers. And the question is it possible to drive from Vancouver to Abbotsford at an average velocity of 120 kilometers per hour without speeding? Right? Is it possible for your average velocity to be 120 kilometers an hour, but for you never to have actually been going that fast? So you have that as your average velocity, but you have your actual velocities not be that. Is that possible?
No.
No. And this is the answer, is no, this is not possible. Now the question is, why is it not possible? And the answer is because average of something is very closely related to the thing it's an average of. It's impossible to have an average temperature of 15 degrees if the temperature is never 15 degrees. It's impossible to have an average speed of 120 kilometers per hour if the speed is never 120 kilometers per hour. And the reason for this is because these things are continuous things. Speed and temperature are both continuously changing quantities. It is possible for the average, I mean, I was going to say it's possible for, like, there's certain things, like, the average family has 2.4 kids or whatever, right? No one has 2.4 kids, right? But that's not a continuously changing quantity. If number of children did change continuously, if you acquired parts of a child continuously over time, then that would be the case. There would have to be some family which had 2.4 kids. But again, not continuously changing, that's the problem. So the mean value theorem is this theorem which says if something is the average, it's got to be that thing at some time. So it says if the average, so firstly, in Calculus 1, you probably talked about one version of the mean value theorem. How many people remember the mean value theorem from Calculus 1? How many people who don't remember it? Like, is there anyone here who never studied it in Calculus 1 at all? Okay. Anyway, it should be part of the Calculus 1 curriculum. It should have been there, but anyways. The mean value theorem is this theorem which says that if the average rate of change of a function is blah, then at some point in the time interval, the function's instantaneous rate of change, the function's derivative, would have had to be blah, that same number blah at some point during that time. So the idea is that it can't have an average of something without at some time being exactly equal to the average. Now, in Calculus 1, you talked about this specifically referring to average rates of change. Remember, an average rate of change is like the slope of the secant line. It's y2 minus y1 over x2 minus x1. The instantaneous rate of change is the derivative. This same thing applies to things that aren't rates of change. So if it's any function whatsoever, if it's a continuous function, again, it has to be continuous because things like number of children in a family is not continuous, and there's nobody who has 2.4 kids. If it's continuous, and if it has an average value, then there must be some point C where the function equals its average value. You can't have an average temperature of 15 degrees without the temperature at some point being 15 degrees. Because the idea is if it was always colder than 15 degrees, then average couldn't have been 15 degrees. If it was average always hotter, it couldn't have been 15 degrees. If it's sometimes colder and sometimes hotter because it changes continuously, it must have been 15 degrees sometime between that time. That's the idea. So this is what the formula looks like for the mean value theorem. It says the value of the function at this point C is the same thing as the average value. So if you can calculate an average value at some point C, then the function must be equal to this average value at that time. Now one thing to mention is oftentimes what we do is we take this formula and we rearrange it. We multiply both sides by b minus a. So what we'll get here is f of c times b minus a equals this integral. What that's telling you is this. I'm just going to draw a picture of a function to make this clear. If we have a function, let's say here is a, here is b. Sorry, let me write that little green part there. This area here, this green area, is the left-hand side of that thing. Right? That green area is an area under the graph. Let's say the average value was here. Let's say that's the average value. And C is the point where the y-coordinate is the same as the average value. Now what's on the left-hand side of this thing is b minus a times f of c. F of c is this vertical distance here. B minus a is that horizontal distance. What that means is if we draw a horizontal line through C and we draw a rectangle here, this rectangle, which is b minus a times f of c, has the same area as the green thing. The red rectangle has the same area as the green curve. So that's sort of one way of interpreting what this point C represents. This point C is the point where the y-coordinate is the same as the average value. If the y-coordinate is the same as the average value, it means if you draw a rectangle through the graph at that point, that rectangle will have the same area as the area under the graph. So those two areas, the area of the rectangle and the green area under the graph, should be the same size. Again, this point, this piece up above should be the same area as that piece down below. Pieces in the green that's not in the red should be the same area as pieces in the red but not in the green. So, here's example 4, and this is going to use some of, this is a question using some of these concepts. So here the function is f of x equals 2x over 1 plus x squared squared. So the first thing they want us to do is to find the average value of that thing on the interval from 1 to 3. So if we want to find the average value, we've got to do 1 over 3 minus 1 times the integral from 1 to 3 of this function. We can do this with substitution. U is going to have to be that thing inside the brackets, the 1 plus x squared. Du is going to be 2x dx. So this 2x dx will become a du. When x is 1, u is going to be 2, because you have 1 plus 1 squared. When x is 3, u is going to be 3 squared, 9 plus 1 is 10. So the 1 over 3 minus 1 will become 1/2. This will become an integral from 2 to 10. The 2x dx will become a u. The 1 plus x squared on the bottom will become a u. That's going to be squared because 1 plus x squared squared. So it's 1 over u squared du. Now if we integrate 1 over u squared, that gives you, this is u to the negative 2. The integrator of u to the negative 2 is u to the negative 1 over negative 1. This whole thing's got to go from 2 to 10. So we plug in 10. We get 10 to the negative 1 over negative 1. We plug in 2, we get 2 to the negative 1 over negative 1. 10 to the negative 1 is 1/10. Divided by negative 1 just makes it negative. 2 to the negative 1 is 1/2. Divided by negative 1 just makes it negative. That negative will cancel it out, so it'll become plus 1/2. 1/2 is 5/10 minus 1/10 is 4/10, which is also 2/5. Multiplying by 1/2 gives you 1/5. So the average value of this guy is 1/5. Right, that's part A. Part B asks you to find a C such that the average value equals f of C. Well, the average value is 1/6, 1/5. F of C is going to be 2c over 1 plus c squared. Right, so what I need to do is I need to solve that equation. I need to find that c such that equation is true. I'm going to cross multiply 1 plus c squared equals 10c. So the thing I'm going to mention is if you take this equation, you try to solve it, it's going to take you a whole lot of work to do. So the easier way to actually solve this thing is to actually pull out your graphing calculator. And what you can do with your graphing calculator is, I'm just going to pull out group plot. I want to see when those two things cross. When 1 plus x squared squared, when does that cross the graph of 10x? Well, there we go. I can see that point. Oh, so the first thing to mention, if you look at this, or let me do it actually, I can just do it with the original function. So 2x over that thing and 1/5. That might also make a bit more sense. There we go. Where's my zoom in window? There we go. Okay. So here's the graph. So this is the graph of the function we're finding the average value of. This point here is the average value, that line there. Now we're not interested in finding this point here. The reason we're not interested in finding that point there is because that point is outside of the interval in question. Saying it took on its average value back at 0.1, that's not interesting to us. We want to know where in the interval from 1 to 3, where in this interval does it take on its average value? And so we've got to go over. And we'll notice at 1.8, it takes on its average value. So C here is going to be 1.8. It's going to be this number here. So if we sketch the graph of this thing, the graph looks like that. The average value is 1/5. Oh, let me just make this a little bit. At 1.8, the y-coordinate is equal to that average value, right? So if I want to sketch a rectangle which has the same as the area under the graph, well, I could draw this rectangle here. That rectangle should have the same area as the area under the graph. Right, the rectangle of height 1/5 and width equal to that region. So again, just to illustrate with my different colors, this red area should be the same, if I draw the graph accurately enough, as the area I'm going to color in blue. That blue area and the red area should be the same. When we draw a rectangle whose height is the average value and whose width is the interval we're talking about, that should have the same area as the area under the graph in that interval. So any questions about example 4 here? Again, by the way, where the mean value theorem comes into this is the mean value theorem is what guarantees you that you can find such a C. The The mean value theorem says that this point C exists, that you can, if you do the work, you can actually find a point where it is the same as its average value. So this is sort of asking you to verify the mean value theorem. So example 5 says we have a function, f, which is continuous, and its integral equals 6. And we want to show that there is some c in the interval from -1 to 2 such that f of c equals 2. Well, the idea here is this is sort of right? Whenever we see sort of f of c equals something, we should always think we should use the average value, right? What is the average value of this thing? Well, the average value, the integrals from -1 to 2, is going to be 1 over 2 minus -1 times this integral. F of x dx, not f of t dt. It doesn't really matter, but right, this is what the average value is going to be. Well, this thing here is 1/3. This integral is 6, as it says on the slide. 1/3 times 6 is 2. So this thing has an average value of 2, right? Since it has an average value of 2, so I can say because f has an average value of 2, there is a c such that f of c equals 2. And maybe it's a good thing to say by the mean value theorem. Right? That's what the mean value theorem says, is if it has an average value of 5, it's going to be some point in the interval where its value is 5. If there's an average value of 10, there's going to be some point C where its average value is 10. That's what the mean value theorem says. Yeah. Boy, this 2 is really, yeah. 2. There we go. And one thing to mention, if I didn't say here that f is continuous, this statement might not be true. It's possible that a function which is not continuous, which has this integral being 6, but is never 2. For example, it could be 0 from -1 to +1, and then it could be 6 from 1 to 2. And if it did that, it would actually still have an average value of 6. Wait, no, it's still have an integral of 6, but it wouldn't have an f of c equaling 2 anyway. But that would not be continuous, and that's the problem. Okay, any other questions about this?
And that statement is on the interval -1 and 2?
Yeah.
Right.
Yes, sorry. Average value 2 on the interval. Yes, you're right. You're right. I didn't actually specifically say that, but yes. Yes, I should have written that in the statement. I wouldn't take off points if you didn't write that in the statement. So, okay, so that's 6 from 6.5. So I just want to mention quickly before I show you folks the group problems. Again, there is going to be a quiz on Tuesday. It's covering everything since the last quiz. So it covers sections 5.3, 5.4, and 5.5, basically what we did last week. And it covers sections 6.1, 6.2. Now again, from 6.2, only those two things could be on there, 6.2.1 or 6.2.2. 6.2.3, 6.2.4, I skipped, and section 6.5. So again, there's a lot of material that could be on the quiz. I will not ask sort of the harder questions on this particular quiz, just because I know it's a lot of material to go over for it. Definitely once comes time for the test, there is a chance that, you might see harder questions, but for now, it's just going to be sort of like, well, I mean, it's not going to be like only easy ones. Again, I said there will be one example of substitution, but yeah. I'm not going to ask like ridiculously hard ones. Again, it's only going to be a 15-minute quiz, so I can't ask any particularly difficult things. And there's a good chance I might ask you just to set up an integral, not to actually evaluate it. Because again, that's a way of me giving you something you can do more easily in 15 minutes. Anyways, so I'm going to show you the group problems. Again, try to work on these. I know if people don't practice doing volumes and stuff, it can become very difficult once it comes time for the quiz. So definitely at least practice setting up the integrals for numbers 1 and 2. Integrals for the volumes. Oh, sorry, 2 just asked you to set it up. In 1, they want you to actually find the volume. Yeah. So anyways, try those guys in about 10 minutes. Yeah, they'll still have time to go over the solutions on the board.